everyone. Now, whatever we have done till now, we are looking into the transient heat conduction problems, and you please don't mix up with that. It is a specific application of transient heat conduction only. The same thing can be applicable to the transient mass transfer or any transient process for that matter. The way I would like to present the stuff whatever I have taught till now, that it should be general enough. You should take it as a general application of whenever you will be facing such equations like parabolic partial differential equations or elliptical equations, and I gave you a general outline of method of solution of those equations given those equations are linear. Okay. So, do not take it as a specific application, but for in context of this course, this is generally applicable to transient heat transfer or transient mass transfer. In fact, we have seen one application in a transient fluid mechanics problem as well, right. Now, we will be extending this discussion on this topic to some of the more complicated equations and in multidimensional form as well. The first example I have with me in today's class is the elliptical partial differential equation. Now, this type of equation you will be facing whenever you will be having a steady state. Please note, this is not a transient problem, this is a steady state problem, but a multidimensional. It is a steady state multidimensional problem. Suppose you are having a block, let us say in 2 dimensional, this is y, this is in x, and you have a heat conduction and it is under steady state. You would like to find out what will be the temperature profile as a function of x and y. So, the governing equation that you will be dealing with, that is basically an elliptical partial differential equation instead of parabolic partial differential equations, that whatever we have discussed so far. The under steady state, the steady state governing equation for heat conduction that becomes del square T del x square plus del square T del y square is equal to 0. In this problem, z dimension is too long. So, all the variations in z direction will be neglected. Now, let us say we have to solve this equation, and this is a linear equation. Of course, we are going to use separation of variable to solve this equation subject to the boundary conditions. Now, you need to have 2 boundary conditions on x, 2 boundary conditions on y to solve this problem. Now, let us say at y equal to 0, you have a prescribed temperature at y equal to 0 means this plane, right. This is y equal to 0, this is y equal to b, right. This is y equal to 0 is this one, right. This is y equal to 0, this is y equal to b, this plane is x equal to 0, this plane is let us say x equal to a, and this plane is x equal to a, right. So, subject to at y equal to 0, let us say t is f x, at y is equal to b, let us say my t is 0, and you need to have 2 more boundary conditions on x. Now, let us have at x equal to a, x equal to 0, t is equal to 0, and at x equal to a, t is equal to 0. Now, this is an idealized condition of the equation and boundary conditions that we are having. In general, all the temperatures prevailing in all the 4 boundaries may be separate. They may be Dirichlet boundary condition, they may be constant temperature boundary condition, they may be Neumann, they may be mixed boundary condition. Now, so that means suppose we consider that there are 4 different temperatures prevail on the 4 boundaries. That means you are encountering 4 non-homogeneities in your boundary conditions. we know how to tackle the non-homogeneity. It is exactly the same method. Okay. First, you have a transformation of scale, do away with one non-homogeneity. So, left over are 3. Now, you divide that problem into 3 sub problems considering one non-homogeneity at a time. So, I am not considering that case only, that case. So, I am considering a base case where let us have we forced the boundary conditions to be homogeneous on all the 3 boundaries and one non-homogeneous boundary condition. That will define my separation of variable problem. Okay. What I mean, if you know the solution of this problem, if you have the non-homogeneous boundary conditions of the other 3 boundaries, you will be able to tackle that, because we have in depth studied that particular case previously in several problems. Okay. So, now you can use separation of variable considering t is a function of x and is a product of x alone and a function of y alone. Okay. Now, you substitute this x and y, this product form of solution in your governing equation, and let us say what you get. You will be getting y d square x dx square plus x d square y dy square is equal to 0, right. So, you can have a separation of variable right away 1 over x d square x dx square plus 1 over y d square y dy square is equal to 0, okay. Or 1 over x d square x dx square is equal to minus 1 over y d square y dy square, right. Now, this is a function of x alone, this is a function of y alone, and they are equal to constant. So, this will be a constant and this constant can be positive, negative or 0. Now, 0 and positive will be ruled out because they will be giving you a trivial solution. So, that will be negative, let us say minus lambda square. Okay. Now, up to this it is there is something to point out at this point. Now, here you will be getting d square x dx square plus lambda square x is equal to 0 as a solution for the x containing part. Exactly, I am coming to that. Now, it depends. Here you will be getting 1 over x d square x dx square plus lambda square is equal to 0. That means, you will be getting ultimately d square x dx square plus lambda square x is equal to 0. Now, let us look into the boundary condition of x containing part. The x containing part must be satisfying the boundary condition of the original problem. That means, that x equal to 0 and x equal to a, your capital X will be equal to 0. That means, it is a standard eigenvalue problem. You have to identify in which direction you will be having homogeneous boundary condition. Now, whenever you will be considering this equation, whenever you are seeking for a solution of y containing part, that will not be a standard eigenvalue problem. You have to associate the lambda square, the constant, with that, such that that part will be constituting a standard eigenvalue problem or a Sturm-Liouville problem. That is the basic idea. That is why I could have associated y with this. That means, I could have said 1 over y d square y dx square y square is equal to minus 1 over x d square x dx square is equal to minus lambda square. In that case, since one of the boundary conditions in y direction is not homogeneous, you cannot have a standard eigenvalue problem in y direction. That is the criteria of the selection. Okay. So, selection is such that you will be having a standard eigenvalue problem in that direction. In x direction, I am having the homogeneous boundary conditions. So, I will be selecting x containing part as the standard eigenvalue problem. Okay. So, let us look into that 1 over x d square x dx square plus lambda square is equal to 0. So, that means, d square x dx square plus lambda square x is equal to 0, subject to at x equal to 0 and at x equal to a, your capital X is equal to 0. Okay. So, these we have solved number of times, and solution is basically lambda n is n pi by a. These are the eigenvalues of this equation, because you can look into the solution, right. X equal to C 1 sin lambda x plus C 2 cosine lambda x, and finally, once you apply these boundary conditions, you will be getting these as the eigenvalues, or n goes from 1 to infinity, and the eigenfunctions are sine functions, right, some constant sine n pi x by a. Okay. So, these are the eigenvectors. Now, let us look into the solution of y containing part. The one y component containing part will be minus 1 over y d square y dy square is minus lambda square. Lambda square is basically lambda n square. So, we will be having subscript yn corresponding to nth eigenvalue. So, this will be lambda n square. So, it will be n square pi square by a square. Okay. So, let us write it at minus lambda n square, fine. So, the governing equation will be d square y n dy square minus lambda n square y n will be equal to 0, right, fine. Now, what is the solution of this? It will be containing the exponential function, right. The solution will be C 1, let us say exponential lambda n y plus C 2 exponential minus lambda n y, that will be the solution. Now, this C 1 and C 2 will be evaluated from the boundary conditions of y containing part, that it will be satisfying. Now, at y equal to b, our t was equal to 0, that was the one of the original boundary condition on y, right. That means, at y equal to b, this is equivalent to, at y equal to b, my y n is equal to 0, right. So, 0 is equal to C 1 exponential lambda n is determined lambda n b plus C 2 exponential minus lambda n b. Okay, fine. So, let us see. So, C 1 or C 2 is equal to minus C 1 exponential twice lambda n b. Okay. Let us see what is y n. Y n is C 1 exponential lambda n y minus C 1 exponential minus lambda n y exponential twice lambda n b. Okay. So, you take C 1 and 1 lambda n b in common. C 1, let us say C 1 exponential lambda n b I take common. Okay. So, this becomes exponential lambda n y minus b minus exponential minus lambda n y, and 1 lambda n b will be there, right. Now, if minus lambda n is taken in common, then again you will be getting exponential minus lambda n y minus b, right. You will be here, you will be getting exponential plus lambda n y minus b, here you will be getting exponential minus lambda n. So, what is that? That will be related to sin h, hyperbolic sine function. Huh?
So, you have two functions, this is C2 of quadrant equation, and then you have another equation called x equal to 0. So, you directly put
You cannot do that. I will tell you that trick later on. Okay. Then you will be getting a trivial solution. Then how to evaluate the final constant, that you will not be getting. Okay. So, let us go ahead with this. So, y n will be C1 exponential lambda n b exponential lambda n y minus b minus exponential minus lambda n y minus b. That is in the compact form, and you can multiply and divide by 2. So, this will be sin each function, hyperbolic sine function. So, this will be twice C1. So, it will be another constant, let us say C1 prime. Okay. So, C1 prime exponential lambda n b sin hyperbolic lambda n y minus b. Okay. Now, my solution is now the product of x n and y n, because I get all the x n's, I get all the y n's by using principle of linear superposition. You add all the solution and sum it up, right. So, if you do summation x n and y n, you are having two constant. With x n you will be having, let us say, some constant c times sin n pi x by a, and here you have C1 prime. Multiply of the two constant, you will be getting a new constant. Let us say summation C n sin n pi x by a hyperbolic sin lambda n is basically n pi by a. So, you can write it n pi by a y minus b, right. Now, the only the whole solution is complete. The only thing that is left is evaluation of this constant C n. Now, for evaluation of that constant, you will be evaluating the non-homogeneous boundary condition, that is at y equal to 0. Okay. So, it is exactly the same way we have solved a parabolic partial differential equation with non-zero initial condition and homogeneous boundary condition. So, non-homogeneous initial condition is used to evaluate the ultimate constant. Similarly, in this case we will be evaluating this constant by applying the non-homogeneous right, it will be there exponential lambda n b, right, exponential n pi b by a. No, that will not be constant, because that will be containing n. That will be containing n, and this summation c is over this subscript n. Okay, so it is basically running index. So, it is not a constant as far as this summation is concerned, because it is from n equal to 1 to infinity. So, applying the non-homogeneous boundary conditions on y, you have to evaluate this C n using the orthogonal properties of sine functions. So, what is that? At y equal to 0, your t was equal to some prescribed function f x, let us say kx, kx square, kx plus c, sin kx, whatever it is, okay, or constant maybe, it may be t1, let us say. So, if you do that, then it becomes, let us say f x is summation of C n sin n pi x by a exponential n pi b by a sin h n pi by a y minus b. Y is 0, so it will be minus b. Okay. This will be sin h minus n pi b by a, right. Now, multiply both side by sin m pi x by a dx and use the orthogonal property and see what you get. So, I am just omitting one more step and writing the final expression. So, you evaluate the open up the summation series, apart from only one term, all the terms will be cancelled out because of the orthogonal property of the sine function. So, this is from 0 to a, domain of a. So, f x sin n pi x by a dx, right. And as far as this integration is constant, this term and this term will be treated as constant, they will be coming out of the integration sign, right. So, it will be exponential n pi b by a sin h minus n pi b by a integral 0 to a sin square n pi x by a dx. And what will be this? This will be a by 2, right. This integral will be a by 2. So, probably you will be getting 2 by a, all this denominator, I am just denoting it by d and then the numerator n. So, if this f x is constant, you can evaluate the numerator. If f x is given in any standard function, let us say kx plus c, okay, whatever, you can evaluate this integral analytically. If you have a complicated version of f x that you have, then analytical integration may not be possible. You can do a numerical integration and get the solution. So, C n will be obtained. So, you can get the complete solution once you put the solution. Again, you see that whenever you will be computing the temperature profile at any x y location, let us say you are having a 3-dimensional plot t versus t as a function of x and y. You will be seeing beyond 5 or 6 eigenvalues, the contributions of various terms will be negligible towards the whole solution. So, the summation will be evaluated maybe for the first 5 or 6 eigenvalues and you will be getting the solution. Okay. So, this is an example of steady state heat transfer, but multidimensional, 2-dimensional steady state heat transfer. You can apply the same method, that is what I was telling in the very beginning of this class. You can apply the same method whenever you will be facing such problems, not only in heat transfer, fluid mechanics, mass transfer, in any field. Okay. Now, in the next problem, I am having a 3-dimensional problem. A 3-dimensional linear problem. Let us say you are having a heat transfer in a block in 2-dimensional in space as a function of x and y both. In space, as well as you are having transient. So, it is basically transient 2-dimensional problem. So, ultimately it becomes a 3-dimensional problem. So, in total it becomes a 3-dimensional problem. Okay. The form of the equation becomes del u del t is equal to del square u del x square plus del square u del y square. U is basically some scaled down temperature, okay, and there will be in fact there will be some associated constant, that will be thermal diffusivity. Okay. If you remember, that will be the form of the equation, the energy equation that will be boiled down after simplification of various terms. Z dimension is too long, so all the variations with respect to z etc. will be gone. So, there will be some constant associated here. So, it does not matter. Okay. So, I am taking that constant to be 1, there will be some constant multiplied here, that will be corresponding to thermal diffusivity, that we have already done previously. Okay. So, let us consider k is equal to 1. So, that equation becomes del u del t is equal to del square u del x square plus del square u del y square. Okay. Let us say at time t equal to 0. So, you must be having one initial condition on t, 2 boundary conditions on x and 2 boundary conditions on y. So, let us say at t equal to 0, here u is having, let us say, some prescribed function of x and y, or some function of x only, it may be some function of y only, it may be some constant. These are all known functions. Okay. Then it may be function of x and y, it may be function of x, it may be function of y, may be a constant. Let us consider that all the boundary conditions are homogeneous. at x equal to 0, at x equal to a, your u is equal to 0, at y is equal to 0, at y is equal to b, your u is equal to 0. As I told earlier, in a general problem, you cannot have such a well defined boundary conditions. You may be having various temperatures, let us say T1, T2, T3, T4. So, you know how to, so basically these will be giving you non-homogeneous equations, and we have seen in detail previously how this non-homogeneous will be broken down or can be tackled by splitting up the problem into sub problems, so on and so forth. So, I am not considering all those problems in detail, I am just solving a base case. This is basically base case, right. You have one non-homogeneous initial condition and all other boundary conditions are homogeneous. So, since it is a linear problem, your solution can be obtained in a product form of three things. One will be function of x, another will be function of y, another will be function of time only. Okay. Because of this t, I define the temperature as u. Okay, please understand that. So, you just replace these in your governing equation, and you will be getting y times t d square x dx square plus x times t d square y dy square is equal to x y dt dt. You divide both sides by x, y and t, it will become 1 over x d square x dx square plus 1 over y d square y dy square is equal to 1 over t dt dt. Okay. Now, this is a function of x and y only, this is a function of t only, and that will be equal to some constant, and this constant we consider is minus lambda square. Okay. So, we will be coming to let us say we will be coming to the time varying part later on. Let us concentrate on the space varying part. Okay. So, the space varying part is 1 over x d square x dx square plus 1 over y d square y dy square is minus lambda square. Okay. Now, again do a separation of value, you take the y containing part on the other side, you will be getting 1 over x d square x dx square is minus lambda square minus 1 over y d square y dy square, right. The left hand side is function of x alone, the right hand side is a function of y alone, and lambda being a constant does not matter. So, again it will be a constant, let us say this constant will be minus mu square, the either positive or 0 constant will be leading you to a trivial solution. Okay. Now, if that is the case, now let us solve the x containing part. 1 over x d square x dx square is equal to minus mu square. So, it will be having 1 over x d square x dx square plus mu square x is equal to 0, subject to the x containing part must be satisfying the boundary conditions of the original problem. So, at x equal to 0 and at x equal to a, your capital X is equal to 0. So, the eigenvalues are in this problem, it is standard and we have solved this previously, n pi by a, where n is equal to 1, 2, 3 up to infinity. Your eigenvectors are some constant multiplied by sin n pi x by a. That is also we have seen previously, it is mu n, you are absolutely right. This will be mu n is equal to n pi by a. Now, let us look into the y varying part. In y varying part, the equation was, so this is the solution of the x varying part, minus lambda square minus 1 over y d square y dy square is equal to minus mu square. Okay. So, it will be 1 over y d square y d y square is equal to minus lambda square plus mu square. Okay. Now, to have a standard eigenvalue problem, this constant can be treated as minus alpha square. Again, it is a constant. This constant can be treated as minus alpha square. Then only you will be having a standard eigenvalue problem, because you will be having the homogeneous boundary conditions in the y direction.
So if it is negative only, then
Oh, it is minus alpha square.
so
Right.
it is minus lambda square plus mu square. How do we guarantee that that is negative?
No, it is a constant. This constant again can be positive, negative or 0. Against mu square minus lambda square is a constant.
So that means we have to also
The-
put boundary on mu n, a lambda mu n.
Yes, that is definite. That is definite. And later on you will see, just after couple of steps, it really does not matter. Okay. So, if this constant, so again it will be constant. If this constant is negative, then only you will be having a standard eigenvalue problem in the y direction, because the boundary conditions in the y directions are homogeneous. Fine. So, in that case, you will be having 1 over y d square y dy square plus alpha square y is equal to 0, subject to at y is equal to 0 and y equal to b, your capital Y is equal to 0. Okay. So, and let us say what is minus lambda square plus mu square is minus alpha square. So, lambda square is nothing but mu square plus alpha square. Obviously, lambda square is mu square plus alpha square. Okay. Now, what is the solution? What are the eigenvalues? Now, it will be, let us say, m pi by b, right. N is associated with the x direction, m is associated with the y direction. Okay. Alpha n, right, alpha m is, let us say, m pi over b, m runs from 1 to infinity, exactly like n, and eigenvectors are right. Ym is let us say C2 sin m pi y by b, absolutely right. So, what is lambda? Lambda is basically a subscript, let us say lambda m n, because it is a function of both m and n. It is basically m square pi square by b square plus n square pi square by s square, right, under root of that. Since lambda is a function of both the indices m and m, so we write it lambda m n. Okay. So, lambda m means m square pi square by b square, n square pi square by s square, right. So, let us now come back to the time varying part. Okay. If you remember, the governing equation of the time varying part was 1 over t dt by dt minus lambda square. And what is lambda? Lambda is function of both m and m. So, I put the index t, the subscript t m n. So, it will be nothing but t m n dt m n dt, corresponding to mth and nth eigenvalues in your system. So, it is minus lambda m n square, that is nothing but mu m square plus alpha n square. We know this one is nothing but, okay. So, lambda m n square is nothing but m square pi square by b square plus n square pi square by s square. I am not writing it down. Okay. So, what is t m n? T m n will be another constant, let us say C4 exponential minus lambda m n square t. Lambda m n is completely known to us. So, now I put the product. My final solution is u m n as t m n multiplied by x n multiplied by y m. I add all the solutions by using principle of linear superposition and get the final solution. The final solution in this case will be double summation. One summation will be index m, another summation will be over index n. M is equal to 1 to infinity, n is equal to 1 to infinity, and if you remember, all these individual solutions will be having a constant associated with them. So, it will be a product of 3 constants. Let us say this constant is Cmn. So, it will be exponential minus lambda mn square times t sin n pi x by a sin m pi y by b. Okay. Now, what is left? Left is basically evaluation of this constant Cmn. We are having one non-homogeneous initial condition, we will be using that to evaluate this constant Cmn. What is that? At t equal to 0, you are having u as a in general some function of x and y. Okay. So, h x y is nothing but summation, this summation is over m, this summation is over n, Cmn, exponential term will be amounting to 1. So, sin n pi x by a sin m pi y by b. Now, how to evaluate this? Now, you have to multiply both sides by sin m pi x by a sin n pi y by b dx dy, double integral. Okay. So, it is basically double integral h x y sin m pi x by a sin n pi y by b dx dy is this is from 0 to x is from 0 to a, and let us say y is from 0 to b. Okay. Sin n pi x by a sin m pi x by a dx 0 to a integral 0 to b sin n pi y by b m pi y by b dy, right. I multiply both sides by integration, double integration sin m pi x by a and sin n pi y by b dx dy. Now, whenever I will be open up this summation, because of the orthogonal property of the sine functions, all the terms will be vanishing apart from m equal to n for x and m equal to n for y. So, you will be effectively getting Cmn 0 to a sin square n pi x by a dx 0 to b sin square m pi y by b dy, right, that is correct. So, it will be a by 2. No, that is correct, that is okay. C m comma n, that is what the I wrote the, it will be basically constant, okay. It does not matter. So, this will be a by 2, this will be b by 2, so it will be a b by 4, okay. Are you with me, right, all of you? Okay. So, you are having double integral h x y sin n pi x by a sin m pi y by b dx dy. I change the original index of m and n because they are n is associated with x, m is associated with y, and they are basically same 0 to 1, 0 to 1 to n, 1 to infinity and m is also running from 1 to infinity, right. So, Cmn you are having AB by 4, right. So, what is Cmn? Cmn will be 4 by AB n pi x by a sin m pi y by b dx dy multiplied by h x y, right. So, depending on the value of h, you have to evaluate this integral either analytically or numerically. So, if h equal to 1, this will be nothing but Cmn 4 by AB 0 to b sin m pi y by b dy 0 to a sin n pi x by a dx, right. And you know what is this integral? Tell me. 4 by AB. This will be minus cosine. So, minus cosine m pi y by b 0 to b minus 1 is plus cosine n pi x by a 0 to a divided by m pi by b into n pi by a, right. So, it will be AB by m n pi square. So, this AB will be cancelled out. So, you will be having AB by m n pi square, right. Probably this will be the thing. So, Cmn will be 4 by m n pi square 1 minus cosine m pi 1 minus sin n pi. Right? Cos, right, cosine m pi and cosine n pi, fine. So, these when you are having h as a 1. So, whatever the form of h, you can evaluate that integral either analytically, if it is a complicated form, it has to be evaluated numerically. So, you will be getting the complete solution as a function of x and y. Take first 5 or 6 eigenvalues and compute, and you will be getting u as a function of x and y, and you can have a 3-dimensional plot, u as a function of x, u as a function of y, whatever the form it is. Now, in general, if the boundary conditions are not homogeneous, you can split up the problem into sub problems and can get down that problem into the basic base case like this, whatever we have solved. All the boundary conditions are homogeneous and initial condition is non-homogeneous. Then one more typical problem I am having, the first one we have discussed today is elliptical equation. The second one is basically multi-dimensional 3-dimensional problem. There is also parabolic partial differential equations, but 2-dimensional in space. This one is known as the hyperbolic initial condition, HIC. The hyperbolic initial condition, the form of the equation is del square u del x square is equal to del square u del t square. In some applications, maybe heat transfer, maybe transport, maybe mass transfer, maybe or maybe something else, completely different context, you may be facing this type of equation where the domain of x is basically from 0 to L and t is basically from 0 to infinity. This is basically time and this is x, okay, it is bounded condition. Let us say this is transient, this is a hyperbolic hyperbolic partial differential equation. Okay. Now, the typical boundary conditions, that means you must be having 2 conditions on time, 2 conditions on space. The boundary conditions are, let us say, at u is equal to 0, at x equal to 0, and let us say at x equal to L. Okay. Let us say homogeneous boundary conditions on u. In general, as we said earlier, it may be non-homogeneous, but you know how to make them homogeneous. Now, whenever you are discussing about the initial conditions on time, you must be having two conditions on t. Now, when the advantage of any boundary conditions is you know the boundaries, boundary at x equal to 0, let us say boundary at x equal to L, you know what are the conditions prevailing over them. But whenever you are talking about time, you do not know how the system will behave after, let us say t is equal to t at t1. To know the behavior of the system, you should know the complete solution, but that is the final aim. So, a priori you do not know. So, in this case, two boundary conditions on t are defined at time t equal to 0. So, they are basically initial condition. One is, let us say at time t equal to 0, u is equal to f x, and at time t equal to 0, the derivative of u with respect to t is known. The value of the dependent variable, let us say temperature, and its derivative is also known to you at time t equal to 0. Then only you can define this problem as a well behaved problem. Now, whenever you are having the value of the dependent variable and its derivative with respect to time specified at the same time point, because it is at t equal to 0, this condition is known as Cauchy condition. Okay. Now, let us say how many non-homogeneous we are having in this system. There are two boundary conditions on x which are completely homogeneous, two boundary conditions initial conditions on t which are not homogeneous. But since these non-homogeneities are defined at t equal to 0 at the same point, and that too at the initial point, we need not to split this problem into sub problems. You can treat this problem as a standard candidate for separation of variable. If you remember how we solve the separation of variable problem, a well defined separation of variable problem is that you must be having non-homogeneous initial conditions and homogeneous boundary condition. In this case also we are having non-homogeneous initial condition and homogeneous boundary condition. So, although we are having two non-homogeneities here, but these non-homogeneities are appearing at the initial condition. So, you need not to split up this problem. Since the boundary conditions are homogeneous, you are having a standard eigenvalue problem in the x direction as usual. Okay. So, split up is not necessary. The reason I already discussed. Now, let us say u is a function of x and function of time only. After splitting it up, you will be having d square x dx square is equal to 1 over t d square t dt square. And since you are having homogeneous boundary condition in x direction, you define the problem as a standard eigenvalue problem in the x direction. That means, this should be equal to minus lambda square. So, 1 over x d square x dx square plus lambda square is equal to 0, or you are having d square x dx square plus lambda square x is equal to 0. Okay. So, with the boundary conditions of this problem must be satisfying the boundary condition of the original problem at x equal to 0, your capital X equal to 0, at x equal to a L, right, your capital X equal to 0. So, the eigenvalues are, the eigenvectors are is equal to C1 sin n pi x by L, where the n runs from 1 to infinity, and eigenvalues are n pi by L. Okay. Right. Now, let us look into the time dependent part. 1 by t d square t dt square plus lambda square is equal to 0, lambda n is n pi by L. Okay. So, let us see, let us say this t is corresponding to nth eigenvalue, that is lambda n Tn Tn. okay, d square T n dt square plus lambda n square T n is equal to 0. So, again you will be the solution will be composed of sine function and cosine function, right. So, what is that? So, T n will be, you already had C 1, let us say C 2 sine lambda n t plus C 3 cosine lambda n t, right. Now, using the initial condition, we should not evaluate these constants C 2 and C 3, because if you remember, the non-homogeneous initial conditions are used to evaluate the final constant of the solution, right. So, what is my complete solution? Complete solution will be u n is nothing but T n times x n. So, basically u is nothing but summation of u n by adding up of all the solution using principal linear superposition. So, this will be x n is C 1 sin n pi x by L. So, sin n pi x by L, C 1 should be multiplied with C 2, right. Okay, I will write it down again. So, this will be C 2 sin n pi t by L plus C 3 cosine n pi t by L, right. So, that will be the complete solution. Now, C 1 will be multiplied with C 2 giving a new constant, C 1 will be multiplied with C 3 giving a new constant. So, finally, you will be getting u is equal to summation sin n pi x by L C 2 times C 1, let us say this is C 4 sin n pi t by L, C 1 times C 3, let us say C 5 cosine n pi t by L. Okay. At time t equal to 0, now let us now we are having two initial conditions, one on u, another on del u del t at time t equal to 0, and we are having two constants to be evaluated. At t equal to 0, let us say what we have, u was equal to f x or maybe some constant. So, f x is equal to summation sin n pi x by L, this will be off. So, C 5 cosine n pi t by L, and at t equal to 0 means this will be cos 0 is 1, right. Cos 0 will be 1 at t equal to, this term will be equal to 1 at t equal to 0. So, this will be nothing but C 5 sin n pi x by L, right. So, now you multiply both sides by sin m pi x by L dx integral from 0 to a or 0 to L and evaluate, and you will be getting the constant C 5 by using the orthogonal properties of sine function. So, C 5 will be nothing but 2 by L 0 to L f x sin n pi x by L dx, right. So, with a known function of f x, you can evaluate this integral analytically, fine. So, C 5 you come to know. Now, what is left is C 4. For C 4, we use the other initial condition, that is at t equal to 0, del u del t is equal to some h x, right. U was this. So, what is del u del t? Del u del t is summation sin n pi x by L times C 4 n pi by L cosine n pi t by L minus C 5 n pi by L sin n pi t by L bracket close. So, it will be basically summation n pi by L is common, sin n pi x by L is common, C 4 cosine n pi t by L minus C 5 sin n pi t by L, right. And what is del u, the condition at t equal to 0, your del u del t was some function of x, let us say h x. So, put that at h x is equal to nothing but n pi by L sin n pi x by L. Now, at t equal to 0, this term C5 containing term will be off, but C4 containing term will be remaining. So, this will be C4 cosine n pi t by L, right. Cos terms will be equal to 1. So, this term will be equal to 1 at t equal to 0, right. So, this will be the expression. This whole term will be equal to 1 at t equal to 0, you are evaluating this thing at t equal to 0, right. So, again you multiply both sides by sin m pi x by L dx, integral sin m pi x by L dx, and evaluate. So, C4 will be what? 2L by n pi. 2 by n pi, right. L will be cancelled. 2 by n pi 0 to L sin n pi x by L dx times h x. Now, depending on the value of h, you can evaluate this integral numerically. Now, in this, from the first condition we evaluated C5, from the second condition we evaluated C4. Once these constants are evaluated, the complete solution is known to you. Okay. So, this is one of the example of hyperbolic initial condition problems. Now, whatever we have done till now, all are in the planar coordinates, in the Cartesian coordinates, but in sometimes in most of the transport processes are occurring in the tubes or pipes. So, they will be in the cylindrical coordinate. So, probably in the next class we will be looking into some of the examples of the transient heat conduction problems in the cylindrical coordinates. Okay. Thank you. Good morning everyone. So, whatever we are doing in last few classes, we are looking into the solution of transient heat conduction problem, or in general you can convert all the analysis into any transient transport phenomena problem, right. Whether it is a heat conduction or whether it is a fluid mechanics problem, it really does not matter, because the way we have looked into the solution of various forms of equations with several boundary conditions, all sorts of boundary conditions probably we have encountered, the solution technique was really in general. Okay. So, not necessarily our analysis is valid for the transient heat conduction problem, it is valid as well for any other transient transport processes. Now, whatever we have done till now is basically 2-dimensional or 3-dimensional conduction problems in planar coordinate. Now, in a typical for the applications of typical chemical engineering problems, the coordinate system may not be well defined Cartesian coordinate system, it may be circular polar coordinates.